Okay, so the recording started and it is the 16th of September 2024, the Western Automation Monday morning technical training session. Our speaker today is Chris Omedian, my colleague at Western Automation. And Chris's subject today is instrumentation and process measurement sensors, which in the automation of the factory and the collection of more data for better factory management is a huge issue, therefore a huge business potential. And Chris is definitely the right guy to talk about it. So without further ado, Chris, it's all yours.
I appreciate it, Pierce. Well, good morning. I don't know if we had new bodies. I can't see the chat here, but don't know if we have good new bodies, but good morning. Thank you, everybody, for joining, sharing your time on Monday. As Pierce said, topic today is instrumentation and process measurement solutions. So where the basis of the topic is going to be sensing for process, but also industrial automation. Our classes were kind of born out of Pierce really getting this thing started, which has been an incredible thing and been awesome that we can start our weeks with our friends out in the field that we work with. So I thought of this, back when we were doing the VFD portion of it. We've done a little bit of a presentation on pressure sensors and some of that, but instrumentation in particular applies to tank level, flow, pressure, a lot of things that can feed back to VFDs. But also for the industrial folks, which I think a lot of us on here are, applicable to, process automation, factory floor, industrial automation as well. As all of you know, we come from a sensing background, traditionally Western Automation as a company with Banner and Turk, and that's one of our specialties, along with the industrial drives design lines. And we tend to focus a lot of conversations on those with photoelectrics, with laser measurement, with inductive sensors, with your traditional factory automation sensors. So I wanted to kind of put a spotlight on what I call instrumentation, which is pressure, temperature, flow, level, and some other technologies that are wrapped around those. I've presented a few times with Pierce in the group here, but please, open dialogue, ask questions. We're doing this for the folks that are on the call. So please ask questions, no dumb questions. I love interaction. If we all just listen to me talk, this is going to be really boring. And it's early, and hopefully you've had some coffee, and we keep it going. There we go. So the general technologies that we're going to overview are, as I'd mentioned before, pressure, temperature, flow, and level. So tank pictorial, you're going to see some more tank pictorials. A lot of the media we're discussing is going to be liquid-based, hydraulic, water, any sort of fluid media. Some of these technologies are applicable to solids and powders and pellets and things like that as well. Just a little diagram here showing going back to that could be a VFD, a PLC, a controller, and maybe if we've got some time at the end, we can kind of discuss how you tie all these in, which would tie back to some of our networking I/O PLC type classes. So sensing technologies that we'll review today. Again, there's your tank, slide number 2. Radar, ultrasonic, pressure transducers, flow sensors. We'll go over those technologies with a focus on calorimetric, which is the product and technology that we represent. Capacitive sensors, which kind of tie back into those industrial type sensors, the inductive. Capacitives have a special place within this process automation world in the tank level or media level sensing. And then again, back with level switch point level probes and temperature. We'll cover a few different technologies. There are a lot of technologies for measuring temperature. The 3 that we represent and we'll talk today are 3 of the most common for picking up temperature on anything, liquid, dry, solid metals, including things like, motors and drives and gearboxes and things like that. So any questions, any other, again, open dialogue sensing technologies that the group would like to hear about while we're together this morning? We'll move on. So we'll start with pressure sensing. Principle of pressure sensing is you can sense air, you can sense fluids, you can sense gases, you can sense different types of substances. In industrial and process automation and the products that we focus on, we have some air pressure switches. The offering is limited. The applications are not nearly as vast as fluid or liquid media. So most of the sensing devices we'll talk about are based around fluid sensing. And you'll see on the right, that's a pressure transducer, in media, which most of them are, that's teed off on a pipe. And to the left of that is a diagram of how that particular sensor works. So the basis of it, on the bottom there, you'll see there's a force or pressure from a liquid or a gas, and then you've got a measuring cell. And we'll look at that measuring cell, I think, in the next slide. That cell basically has a strain gauge on it. So as that media pushes up, the cell is going to flex, and that's going to be either a ceramic cell or a stainless steel cell. And there's different properties of that cell or diaphragm that would make one desirable over the other. But the premise, the technological premise is you've got some flexing, a strain gauge on the back of that. And as the pressure goes up, that device flexes, the strain gauge stretches out, and then you've got some interpreting electronics on the back end that take the output from the strain gauge and will take a millivolt output signal and turn that into something that's usable, which might be a switch point, a transistor switch point, controlling a relay. Most popular would be an analog output, 0 to 10 volt, or more popular, 4 to 20 milliamp for process automation. And we've built some intelligence into these, as with all the other sensors. And again, please chime in if you have questions about the technologies. But IO-Link has become very popular in pretty much everything we're doing in the sensing and automation world. So IO-Link is going to be built into almost all of the technologies, other than some of the simple ones we're going to talk about at the end of the presentation. So you'll see at the top of that strain gauge, you're converting a mechanical force into an electrical signal that's consumable by your PLC, by your VFD, by whatever is going to use that signal to do something with your process. A little look at two of the most common types of pressure sensors. These two happen to be from Turk and pretty typical from a lot of the industrial and process automation suppliers. You've basically got the one on the right there with a process fitting on the left and a quick disconnect on the right. That would be a pressure transducer. And then we refer to the one on top as a pressure sensor. That's essentially the same package as the device on the right with some advanced electronics. You can see the LCD. It's programmable on there. You can read it out. You can set alarms. You know, the LCD display will turn red when you go past trip points. You can configure the device. You can lock it out on that display.
Hey, Chris,
yes, sir.
I got a question.
Yeah.
The big players in this market, I'm assuming Turk is one, but who are the other guys who I hear names like Maymac?
They're a small player, and thank you, Chris. That's a really good question, and a lot of what we're doing today is sort of technology, but I do want to discuss with our partners on the call here, who are our competitors, where do we fit, how does it go? So great question. The leader in this where we play, so from a lot of these technologies, there's sort of two buckets. There's the super high-end bucket, which is in process automation and some factory floor, which is Yokogawa, Emerson. It's the really high-end, very extremely precise measurement devices in pressure, in temperature, in flow. And those devices, which are typically a heart output, you're talking $5,000 to $10,000 per sensor. Now, Chevron probably needs that for their oil process. Do the guys that are, taking water and putting it into a mold machine need that? Do most of the folks out there need that? No. And you will find a lot of applications where people, they know those high-end names, they trust them, they've got good name brand recognition, they'll buy them, and they don't necessarily need that accuracy. So the other bucket besides those high-end guys are sort of what I'll call the industrial sensors that are also applicable in process. And that's where Turk plays. You'll see some banner sensors here as well. Our biggest competitor in the process world is IFM. They're a good competitor. They make good products. They sell direct only, and they employ a direct sales force that are empowered to. They've got good products, and they are empowered to almost do what they want with pricing. So we'll run into them. They're a tough competitor. We can beat them, but we've got to have boots on the ground. We've got to have the information of, what are the price points and what are we doing. So IFM, you'll see probably more than anybody else. Aside from that, you'll see Balluff. You'll see, the big guys. I want to say Siemens. Some of the big guys will have an offering of this that's probably labeled. IFM, Balluff, uh, Automation Direct obviously has some labeled products. Those are the folks that you're going to run into the most on this product, and they're going to look a lot like ours. You're going to know if you look at those two pictures, if this is a new technology for you and you're walking a factory floor or a process floor, you're going to see if it's not a Turk device, you're going to see something from Balluff or IFM or one of our competitors that looks almost identical to that guy with the LCD screen. And we have way more competitors on the pressure transducer on the bottom right. It's a lower cost, simpler device, more cost competitive, easier to manufacture. It's basically a cell, an electronic, and a connector. So, Weka, transducers direct. There are 50, and I'm probably aiming low, different people that make those, but they don't have the name brand recognition that we do.
And
Um,
the smaller one on the right, on the lower right,
mhm.
is what, a 200 $300 sensor as opposed to your $15,000 sensor?
Correct. So the one on the bottom right, and that's a fairly new product from Turk. They had the previous generation gave you the same functionality at about double the cost. And so it was a tough sell. Unless they loved the folks on this call, they could find something that could get the job done, and we just weren't competitive. This new line on the bottom right, which I say new now, pre-COVID, 5 years, very competitive, very robust. We want to go after those. Those guys list price, depending on the model. I think we're in the $160 price range, list price with room to move.
Oh
Some
my
of our
gosh.
competitors, some of our competitors are well under the $100 mark, and that's not a problem. We just need the feedback.
And then the sophisticated sensor with the digital display lists
Mhm.
roughly.
Yeah, so that guy, same story. We sold a lot more of the predecessor of that, but the predecessor was in that $700-800 range. The new one, which is much higher performing, you're in the $500 list price range, and that is an IP69K, no moving part, unless you consider the diaphragm, no moving parts within that. Those buttons are capacitive, so you can high pressure, high temperature wash down that thing in food and bev. It can sit outside on a pipe. It's a super robust guy, and it's at a very good price point, but you pay another $350 to get that display, to get that functionality, to get the programmability, and you can see some of the stats or features of it here. Accuracy, IO link. You can you've got the higher IP69K rating. You can invert the display. You can rotate the body around. So that's more of a flexible guy. I would say this guy isn't as a user product. Some OEMs, if they're building a skid, may want that. And the guy at the lower cost, simple guy, that's more of an OEM product where, your cost is going to be good. You're going to get the signal you need for your machine, but you don't necessarily need all of the electronics.
And one final question, you mentioned heart.
Yes. Yeah.
That sounds
So
like a sophisticated protocol.
it is not, but it's very unique to the process automation world, and it's not something that we output. So Heart is, I don't think in all of my years I've ever seen it implemented on industrial factory automation floor. If you talk about the Chevrons and maybe some of the pharmaceutical guys and the traditional core process folks, they like that Heart signal. It's a two-wire digital, kind of sort of like IO Link. It's been in the process automation world. I'm going to take a guess because I don't live in that world, but I bet it's a 25-year-old technology that's been being used for 25 years in the process automation world. So
Thank
that
you.
might be a reason they go for the more expensive sensor, even if they don't need the accuracy, unless they were to get an analog to heart converter from an industrial sensor from us or IFM or Balluff or one of those guys. And that's really the only protocol that we're not going to talk about today. But it is out there. You will hear it. and we have a workaround for it if you come across it, if they don't need that super high accuracy. You'll see on this device, you're 0.25%. The other guys are in the 0.05% range. You know, they're a quarter to an eighth of our accuracy in those devices. But again, you're talking a $500 sensor versus a $7,000 sensor. So just going through some of the general specs. It's funny. I always think I'm going to have a short presentation and got to keep an eye on time here. Um, just general specifications. We talked about ceramic, stainless steel diaphragms. Ceramic, usually used in lower pressures, more brittle. So within a pressure sensor, you'll hear a burst pressure, and that is the pressure above what it's rated for that this device will take before you are at risk of cracking or damaging that cell where your output now doesn't function correctly. So oops, ceramic is a more um, brittle and more solid diaphragm. Stainless steel gives you a little more flexibility, more for higher pressures, typically has a higher burst multiplier. So a burst pressure will come in a multiplier of rated pressure. So if it's 100 psi and you've got a 5x burst here, it'll take up to 500 psi. You might have a 8x burst pressure on a stainless steel diaphragm. Ranges for our products are vacuum, which is a negative pull or a vacuum, up to 15,000 psi. And a lot of people don't know that we go that high. For HPUs, some high pressure hydraulic type applications, we cover the gamut, and we have thousands and thousands of iterations when you go through our part number configuration of, you know, different pressure ranges. We do PSI, we do bar, torr. We've got a lot of different ranges that we offer there. And then those combinations come in with the process connection, which is this on the bottom. That could be G quarter, NPT. We do some UNF or SAE, which is like an automotive connection. So we've got a host of different connections. This is just a sampling from one of our products. But when you hear process connection, that's this device on the bottom or the left. And then connector type would be M12, you know, maybe a 7/16, or for like mobile automotive, we'll do Deutsch connectors. So we've got several different connectors on here that are sort of driven by industry. And then finally, electrical output, which kind of similar to most of our other sensors. You know, you've got your discrete IO link, analog. We've got a couple of other specialized outputs on these guys as well. So any questions on pressure? All right, moving on. Temperature, RTD. So temperature, there's several different technologies to measure temperature. RTD is one of those technologies, what stands for resistant temperature detector. And this is basically, typically they use platinum as a metal. It's a sensor where the resistance changes based on the temperature. And there's a lookup or calibration chart based on what that metal is used. There's ones that use copper and brass and other metals. Platinum is the most common. And it's a pretty linear graph that says, hey, when it's heated to this temperature, you're going to get this resistive value output from that device. And I would say RTDs are the most popular temperature sensing device as far as volume out there in both process and industrial automation. With those RTDs, traditionally, an RTD device is very simple, it's very inexpensive. And so you'll have that probe that's deployed. The issue with an RTD is you get a very low level resistance value that changes with temperature. So with that output, most people will buy, it looks like a puck that they put in their enclosure, and that puck can be a couple few $100s that needs to interpret that resistance value and now give you your 4 to 20 milliamp or 0 to 10 volt or whatever your signal output is. They're big, they're bulky, they're expensive, and that's how people have done it for the last, I don't know how many decades. And you'll see down here, it generates a voltage, one milliamp or less measuring current. So it's a very low level signal. We do offer plain RTDs if people want to use a puck or they have an interpretation card in their PLC or IO block. We can offer RTDs. Our solution which we find a lot of people love, is to not take that traditional RTD with that weird low-level signal where they got to buy a special card for their PLC or their IO rack, but go ahead and take care of that conditioning within the device and just give you a 4 to 20 milliamp output or a 0 to 10 volt output. So if you look at this diagram here, this kind of shows evaluation of the device, which is your head unit. And again, you'll see in pressure, temperature, flow, you'll see that same form factor with that IP69K capacitive button LCD. The interpretation electronics are a little bit different. The head unit's the same, and it really looks the same. We've got our M12 on the front, and then a temperature, flow, or pressure probe on the bottom. Another iteration, which is a really cool product that really, we have to have competition out there. I can't tell you who it is. It's our TTM product, and we take the RTD probe with that low level signal output here, and we will integrate an M12 connector with a flexible circuit board on it, and that can be separate with the remote probe, or it can be integral. And now you've got your RTD in the tip here, and here you've got your electronics built in that's doing all the interpretation, and now you're a 4 to 20 milliamp signal from here back to your PLC. So you eliminate the puck in the panel. You probably add, call it $100 for something like this, and an RTD is a very inexpensive device. You eliminate the puck, you eliminate the card and the PLC, and you've got an all-in-one package. So it's a really cool, unique solution. Honestly, I don't know why we haven't been knocked off by a bunch of competitors. It's a unique way to do it. And you'll look at the pressure measurement ranges down below, and these are specific to our products. On the base devices, our standard devices, you look at our portfolio, 80% of our offering is negative 50C to 150C, which equates to negative 58F and 302F, which is fitting for a lot of industrial applications, a lot of process applications. You get into some applications with furnaces, heating, molten metal, that sort of stuff. With these devices, we can go from 0C up to 500C, which is 932F, which is, I don't know how many of you have seen applications above 1,000 degrees Fahrenheit. They do exist. We'll talk about another technology here in a minute, which is thermocouple, which can get you well above that. So we've got a host of products to offer that should be able to suit most applications. Any questions on RTDs or TTM? I left out, I'm realizing, let me see if it's in here. Yeah, I left out the data sheet or the pictorial of our temperature sensor, but it's identical to this guy here, which is our pressure sensor. So same thing with your RTD probe, and it's spitting out a 4 to 20 milliamp programmable LCD color change, similar functionality, different measuring principle. Questions on RTDs? So we mentioned thermocouple. I would say this is the second most popular means or technology of measuring temperature. Thermocouple is another sensor that measures temperature, and basis of this is you've got two dissimilar metals, and when they're heated or cooled, a voltage is created. So similar concept to RTD, but rather than measuring resistance, you're creating a voltage that's produced from the thermal change in the two dissimilar metals. These are very inexpensive. They're robust. They're cost effective. RTDs tend to react much faster than a thermocouple. You'll see users, a lot of our OEMs use RTDs. If you have a lot of temperature sensing, like I've seen ovens or autoclaves or things like that, where they need to have 50 different temperature points, they'll have a device. This is one form factor most popular. You'll see this little yellow connector with the two prongs and then a probe. They'll have 50 of these within a chamber. And this is a very inexpensive device. The catch with a thermocouple is it's slow to react to temperature changes, which may or may not be okay. Your other trade-offs for that low cost are based on that low voltage output, you have to have a specific material that is calibrated to mate to that sensor here to get back to this device to make sure that you're getting that voltage output here at that thermocouple. And then again, you need a special card to interpret that. So this portion of the picture, very low cost, but you've got some things to be aware of, which is the cable and then, interfacing with your PLC process control or machine controller. Questions on thermocouples? Third portion of temperature sensing is non-contact. So contact, great. You need to be right in the media. Really, if you're trying to get the most accurate, you want to be in the media. There's some applications where that's just not a reality. You can't do that. There's no way to get to it. It's enclosed, whatever. You don't want to touch it. It's something, it's pharmaceutical, it's food. You don't want to have anything in that media that could grow bacteria, that could cause issues with the product. Then we would look at a non-contact temperature sensor. We've got a few different offerings. These are all from Banner. Turk has one as well. The main basis of the technology, so we talked about RTDs, we talked about thermocouples. Main basis of the technology for non-contact is usually infrared technology. So you'll see these two on the top. These are infrared sensors. This is a low-cost way to have an amplified signal output without touching the media, and now you can measure that temperature. So think, a tank with hot water or some hot media in it, or a motor or a device that you want to measure what's going on. You want to measure temperature runaway on a gearbox, something of that matter. You would use something like one of these devices on the top, and the range is a little bit smaller than the RTDs or thermocouples, but they still cover a pretty good range. Negative 20C, negative 320C, which equates to negative 4F or 608 degrees F is your range. So call it 0 to 600 degrees Fahrenheit. We can measure with these non-contact devices. They are non-contact, but infrared is a light source that measures heat. So you can imagine your limitation is going to be range. So this little guy on the right, I'm going to take a guess, and it is a guess. I think this is a $150 sensor. Infrared output here, Modbus output with register values of what that device is. The measuring range of this guy is 3 to 500 millimeters. We've got a more robust industrial metal barrel sensor with some specialized lens and glasses for high temperature on the front of this guy. It'll go out. This is our long range one, again, at 1 meter. So you're talking 3 feet. You've got to be close to what you're trying to measure. And then finally, from a temperature standpoint, little different technology, looks the same, slightly different application. This is a temperature and humidity sensor. So this would be more for environmental monitoring in a food plant, in a pharmaceutical plant, in an area where you need to monitor, you're producing something that the temperature is going to affect the process or the product. Again, a very inexpensive, I'm going to guess again, $250. And now you've got a ambient temperature measurement as well as a relative humidity measurement. So also, we see these applied in pharmaceutical a lot. They need to know if there's moisture in the air. They need to know what the temperature is. We see them in food plants, chip manufacturers, people that make potato chips. If you're in Georgia in August, your chips are going to taste different if you're not conditioning the air than they would in Southern California in August, right?
And Chris, what's the resolution of these sensors?
They're generally, from a temperature standpoint, I can pull a data sheet, but I'm going to say, your resolution or accuracy is about 0.2%, I believe. So you're in that range. They're pretty accurate, but you're not in the fraction of a degree, right? If you look at that range, it's a percentage of the full range. So you're within a half of a degree to a couple of degree resolution, which is good enough for most applications.
This sensor at the bottom where you have temperature and humidity.
Mm-hmm.
I need to talk to you about that because right now I'm wrestling with large electrical enclosures that have to be kept above the dew point.
Yes, exactly.
And the two determining factors for dew point are temperature and relative humidity.
They are. And so we can do exactly that, Pierce, with this device. We also have, which I did not include in this presentation, we have a dew point sensor with Banner Engineering.
No way.
Yes, sir. Yes, sir. So give me a call afterwards. I love this. This is why we do these meetings, right? We're trying to get the brain juices flowing and ideas, and those missed applications or current applications. So I'll make a note, Pierce. Give me a shout. I know we got to talk about a couple of other things today, but I'll shoot you a data sheet on dew point.
Yeah, for the class, I'll just briefly describe this application. We're having many, and when I say many, probably a dozen in the last 2 months, end user customers contacting me regarding problems with condensation inside electrical enclosures. And it's not just along the coast. The wide temperature ranges in the desert will do this also. And the definition of dew point is the combination of temperature and relative humidity. Above the curve, you're fine. Below the curve, you start getting condensation.
Yeah,
And
I
it
like to
condenses
use.
on.
Mhm.
Go ahead.
I was going to say, I like to use the example of the ice cold Coca-Cola on a summer day. When you step outside, what happens to it?
Yep, exactly.
You get water
And
formation on the outside. Yeah.
yeah, and water formation on circuit boards and water formation on conductive surfaces. And um, this happens to be along an area that Chris and I work in quite frequently, which is variable frequency drives, which are frankly blowing up because the enclosures aren't designed for avoidance of the dew point.
Yep.
So big market for that.
I'd like to
Hey,
change my.
Chris and
Yeah.
Pierce, you guys also, Turk also has the control cabinet monitoring module
Yes, sir.
that's really meant to go in the cabinet. So that's it's the IM series. It's out of Europe, a little hard to get here in the US, but I've looked at it a few times too. So
Yeah, it's a killer
Oh, thanks,
product.
Ernie.
Yeah, thank you, Ernie. It's a killer product, and it'll tell you if the door is open. If somebody,
yeah,
excuse me, leaves the door open on the enclosure where you can get crap coming in, and it will measure temperature. I don't know if it does dew point, but I'll check. And that would be
it does humidity too. It does humidity too, Chris.
Thanks for
Wow.
teaching the teacher, Ernie.
Yeah, so Chris, we need to talk after class, and if anybody else is interested, drop Chris an email, and we'll send you the results of our discussion.
I'd like to change my Coke example to an ice cold beer on a hot summer day.
That'll work.
One other application, and Ernie's certainly familiar with this. Thanks for joining, Ernie. I can't see the class here while I'm in presentation mode, but dew point is also applicable to process air. So yes, enclosures, making sure your electronics don't get wet if you're in a humid, muggy environment, but also process air where you're running air down to your machines, compressors, etc. If you hit that dew point, you're potentially introducing water into your air lines, which can be catastrophic to the system. So the dew point sensors are very popular for that as well. Flow. I'm gonna keep chugging along here because I definitely don't want
You
to.
missed one other key market though, Chris, and
Yeah.
it's huge here in California. That's the cannabis market.
Great point for temperature and humidity. Absolutely.
Yeah.
Absolutely. Absolutely. I'm feeling like there's a little bit of a resurgence. I mean, it went nuts 5 years ago, 4 years ago. I think it got saturated, and I'm starting to hear from folks that are reemerging. I think some people fell out of the market, so I'm hearing from that industry again now within the last 6 to 12 months, which is good. Flow.
Jared's on the call. Jared, our buddy Steve Barberry is give me a call about that. He's got an application that I can talk to you about.
Okay, so flow, I'm gonna kind of chug through this one. We don't see as much flow, but I want to touch on it, and I don't want to run over. I've got a few slides that go into a lot of detail. Flow is measuring the flow of a liquid media that's flowing through a pipe or a process, etc. There are a lot of different flow technologies. You'll see some of those listed here: Coriolis, differential pressure, vortex, magnetic, ultrasonic, turbine, which is like paddle wheel, positive displacement. The three main categories are velocity, differential, and mass flow. We play in that mass flow arena. And again, I'm gonna cruise through some of this, but if you're interested, Pierce usually sends out a copy of this presentation. And as always, please call us. That's what we're here for. If you look at this, if you have an application, you want a little more information or detail other than just kind of the bullets and glossary type stuff that's in the presentation, reach out to Pierce or myself or your Western Automation person. Within the mass flow sensors. So paddle wheel, you'll see a lot. It's literally, the old water wheels you see from the 1800s, 1700s, where they're generating power from. It's a paddle wheel that spins, and you've just got a little counter. As the water or the liquid's going by, it's counting how much is going by, and you equate that based on the diameter of the pipe to a flow. however many ticks come off of that based on the area of the pipe gives you your flow. Fairly accurate device, very low cost device, requires, a counter, a high-speed counter to pick it up. You will see a lot of paddle wheels. On the high-end side, again, like the other ones, you'll see the Emerson, Yokogawas that are very, very high-end, do very accurate, do a very good job. Those are typically magnetic. You'll see some Coriolis from them. Different application, different industry. Again, you're in that $5,000 to $10,000 range as opposed to $500 to $600 range from the device I'm going to show you here from Turk. Let's see, I'm going to skip that one. This is kind of a cool slide. So the devices that we offer, not quite as accurate as the magnetic, the higher end type products. Again, a little bit lower accuracy, but good enough for a lot of the applications that the folks on this call call on. We use the calorimetric principle. I love the diagram on the top right there. It really gives you a look. The basis of that is you've got a small heating element in the bottom of that and a couple of sensors that are going to detect once you generate that heat bubble in there, as the media flows by, what's the temperature as it enters the probe and what's the temperature as it exits the probe? It takes that temperature differential and it can come up with what the flow of that media is. So kind of a cool trick way of doing it. It's been around forever. It's pretty accurate and it's just an economic way of doing, again, a lot of the applications that we all visit. Any questions on flow?
Yeah, what is the accuracy on that?
Let's see if we show here. Let's see if I still have it up. Oops. I can check real quick. Or maybe Pierce, would you mind looking up FS on Turk's webpage? Are you able to do that and maybe put in the chat what the accuracy is?
Yeah, I'll look it up.
Okay, thank you. I don't know that one off the top of my head. I apologize.
No,
Hey,
no
Chris.
worries at all.
Yeah.
This is Chris Keller. I can throw that in the chat in a minute. I have another question in the meantime.
Thank
For the flow sensors that measure actual flow rate and volume, what brand would we typically recommend? Because I know Turk does not offer the volumetric style. Do you know where you guide customers or what they typically use when you want to have an actual flow rate?
Yeah, so we've got several competitors in this realm. Really, this is our flagship offering and product. We do have some legacy products that use other measuring technologies besides calorimetric. We do have some magnetic products. I believe we've got some turbulence products. So we do have something to offer, Chris. Honestly, they're a little high in the price range. So if you've got an application, I can guide you. But if this one isn't a fit, I would say from our offering, flow is one of our more limited technologies. If I'm being honest and looking at all of the instrumentation that we have, this is really our go-to. If it doesn't work, we try and find out, what one of our channel partners, a complementary line that they have to offer.
Got it. Okay, thanks.
Yep. Level. So lots of different ways to detect level. Contact and non-contact, similar to temperature. Technologies we'll go over are ultrasonic, radar, submersible pressure, so pressure again, but as it applies to tank level or media level, capacitive, and then contact level probe. There are other means, but this captures a majority of how people would do level control. We'll start with ultrasonic sensors, again, used in industrial automation all the time for telling if a clear bottle's there or something like that. Also used very commonly in level applications. So the premise of an ultrasonic sensor is you've got an ultrasonic transducer, nice little picture down here. You've got a modulated sound wave. Ultrasonic, it's actually a sound wave that this transducer generates. It's modulated, and when it hits an object, that sound wave bounces back. And you've got a interpreting transducer that measures the amount of time it took that sound wave to bounce off the object. That time then is converted into a distance. So pretty neat technology, been around for a long time, been honed and much better than it used to be, very robust. These can give you discrete analog IO link, our traditional signals that we all work with here. Ultrasonics, lower cost for an analog output. than some of the higher end laser sensors, and really good for specialty applications, clear objects, liquids, which don't work with photoelectrics or light sources, as well as solid sensing. You know, some pellets, some things like that, where they don't shine would be like very loose powders that would absorb a sound wave. They must be used at atmosphere. They don't work in a pressurized tank. You kind of funk up those sound waves. And then another thing just to be aware of with an ultrasonic is the target needs to be perpendicular to that sound wave. If you look at the bottles there, it needs to be perpendicular. They get a little bit of play. You know, our sensors, including our competitors, they have a lot of variance. We've got, I think, the most variance as far as the industrial automation, but I would say in general, plus or minus 15 degrees, which isn't a whole lot. So if you've got, you know, a plate this way or, you know, a really small round object, those sound waves, if you look at the picture, you can't see them, but if you kind of imagine in that picture, those sound waves will bounce off the item and not return the signal to the transducer. And that's why you've got to have almost a perpendicular target. Great product, cost effective, robust. They've been dialed in. Another thing to be cognizant of is that they can be affected by temperature. They can be affected by humidity, rain, and snow. So not good for outdoor applications, generally speaking. There are some workarounds for it. Or, you know, I've had some applications where people have been cooking masa for a tortilla line, and they're trying to shoot this thing over an oven that's 1,000 degrees. That thing's going to freak out. So just some things to keep in mind when you're thinking about this. We've got a very long range ultrasonic, one of the longest range in the industry. The one on the bottom there that goes out to 8 meters. We've got some smaller, more accurate ones that go out to a couple 100 millimeters. The other thing to be aware of is that beam sort of looks like a football if you go out to the range of the sensor. And so you want to be aware of what we call the effective beam width. And if you're able to see your screen, you'll see kind of that football shaped pattern is the effective beam width. That is the sound wave. So you want to have your target within that beam, and you don't want to have any obstructions within that beam. So if you're in a vessel, you need to make sure that your effective beam is more narrow than the vessel. Otherwise, you get subject to sound waves bouncing in directions that you don't want. And if you refer back to the diagram of shooting that thing out, measuring the time and coming back, you can imagine if you do a billiard shot off the side tank and off the bottom and back, you're going to get a super weird value. So just another thing to be aware of, that effective beam pattern, and making sure that you've got a robust solution for the application. Outputs, same as everything else. Transistor, analog. These ones do have that big guy's got a relay output, so you can do some pump in, pump out applications for tank, where it's all self-contained. You don't need a PLC. And then IO-Link, as with everything else. Let's see.
Hey, Chris.
Yes, sir.
Just getting back to an original other question.
Yeah.
It looks to me like the response time is anywhere from 3 to 6 seconds on this size 100 FS unit, and the switching point accuracy is plus or minus 2K, which I'm assuming is 2 degrees Kelvin.
Yep.
And the reproducibility or repeatability in another way of saying it is 0.5K.
There you go. There you go.
So I'll send this data sheet out to everybody.
Thank you.
As well as your presentation.
Thank you, sir. Principles of radar. Again, we're going to run out of time here, so I'm going to scoot through some of this. Radar stands for, I kind of like this because a lot of people don't know, why do we call it radar? Radio detection and ranging. There's several technologies. The ones we represent use FMCW and pulsed technologies. Radar operates sort of from a pictorial standpoint similar to ultrasonic, where you've got a beam going out and it's measuring the amount of time coming back. Radar used to be magnitudes more than ultrasonic. Both Banner and Turk offer these technologies, and the cost of these have come down fractions of what they were 5 years ago, and certainly 10 years ago. I mean, radar sensors were in the thousands of dollars. Now we've got some short range devices that are in the couple hundreds of dollars, and even some of our very capable devices. This is a very popular one for tank level. You're looking at $500–600 kind of a thing. This is a great technology for non-contact tank level, non-contact detection, crane collision avoidance, picking up large objects, detecting items out in the field, and giving you a positional feedback. It's a very robust way to do it, a little bit more than an ultrasonic, but really a bulletproof technology. And I would say from a sensor standpoint, this has been in the last 5 years one of our real push products and something we've sold a lot of. We're much lower than our competition in this segment. Advantages, why you pay more? Immune to humidity, rain, and snow. Extremely long range. We've got that guy in the bottom will go up to 100 meters in range. What you would sense at 100 meters away, I have no idea, but we have it. These can operate in pressurized tanks, and they're software configurable. So now, you know, that effective beam pattern on the ultrasonic, you can change the thresholds that it's looking at. You can change, you know, the trip points. You can change the area that you detect or allow that signal to bounce back. And then the guy on the right, we've got in a 1D and a 2D version. 2D just quickly because it's a new product and it's cool to talk about. That radar offers a 2D plane where it can detect multiple objects, feedback velocity and position within the defined field of the radar. So unique applications, but if you've got them, I don't know that there's anything else on the market at that price point that can do what that guy does. Contact radar. It's actually a microwave technology. It's referred to as guided wave. And again, the high-end folks that are in the process automation world, they've got these, same sort of deal, much more accurate, you know, for critical applications, very expensive media, much more expensive. And this picture actually is one of the high-end guys. Ernie might recognize that picture there. This is one of the high-end guys that does it. We have our own version of it as well. Little lower accuracy, more applicable to your standard industrial automation applications, much more cost-effective. The premise of this is you're basically sending, again, use that pictorial of the wave going out and back. Now we're using a probe. It's called guided wave because you're guiding that wave down this probe. The wave is contained within that probe, and it will bounce the signal back based on where that liquid level is at. So that probe's going to be the depth of the tank, and your wave is going to be bounced off of wherever that liquid or media is at within the probe. So as that goes up and down, these signals come back faster up here, and it takes it longer to get down to here or here and bounce back and give you that analog output. Popular for tank level, you know, different medias. This is a picture of our level sensor, Turk's level sensor. There's your probe there, up to 2 meters in length. So these are not for huge tanks. Some of the higher end guys can go much farther. You know, we kind of aim for that 80% of the market. What can we serve? Accuracy plus or minus 5 millimeters. And some similar features to our other ones. You can rotate this thing, I/O link output, analog. You can get switch alarm outputs. And then we've also got this device here, which is a coaxial tube, which would go around this. It's used for specific media. And I'm actually working an application now where we're in a hydraulic tank where they are cleaning that tank all the time. So the tank's got waves of fluid in it. You know, these could be 6, 8, 12, 16-inch waves in there. Non-contact's is going to freak out. Having this tube around there, this sort of tempers down or mitigates the fluctuation in the waves as they hit the metal tube, but the fluid rises and lowers based on going through these small ports or holes in the side of it. Submersible pressure. So yes, it's pressure, but it's used for tank level. These are a couple of different styles. Basically what you'll see here, similar guy here, it's very similar to the pressure transducers we started today with. However, you'll have a weight here that brings us down to the bottom of the tank. This is what they call a bullet. This will sink it to the bottom of the tank. The media goes in that little hole, and you get same thing. You've got that diaphragm in there that's going to flex the strain gauge based on how much pressure is there. These can also be ported in a standard pressure transducer at the bottom of the tank. Now, the premise is a pressure transducer gives you an amount of pressure, right? So if you're measuring air or liquid or whatever in a pipe, you're going to get a pressure output. With a tank, you put it at the bottom of that tank, either, you know, through the side or drop it in with that bullet, and you're going to get a pressure with gravity as that tank level goes up and down that pressure is going to go up and down. So you basically create a table. This is an inexpensive way to get an analog output on a level. As that goes up and down, you create a table that says if my pressure is X, my tank level is Y. Does that make sense? Any questions on pressure or guided wave radar? So those all offered analog. Some folks just need a discrete signal, and we're going to wrap up with two types of discrete signals. This would be a capacitive sensor, and these would be mounted on a sight glass or the outside of a plastic or poly tank. And as the media passes that sensor, goes up and down, that sensor is going to output. Capacitive sensors are based on differential and dielectric constant, which is a property in all materials. We've got lookup tables, and it will switch. So if you've got a thin plastic container that it's on, and let's say the dielectric constant of that poly is 1.5, and you've got something, some sludge that's got a dielectric constant of, I'll make a number up, that's 10. As that level goes above where the sensor's at, it's going to trip off. So you're only going to get, I'm at this point on the level. A lot of these applications are going to be a high warning, a low warning, and maybe you've got something in the middle. Some folks will sort of array them to get 3 or 4 readings out. Very, very immune to EMC, low cost, easy installation. You're not piercing containers. You're looking through plastic, looking through sight glass. It could be liquids, it could be solids, it could be powders, which are difficult for ultrasonics, radars, and even photoelectrics. So a problem solver for powders as well. There's a picture of our most popular, Turk's most popular capacitive sensor looking through a glass tube, sort of a sight glass that's on the exterior of a tank. And you see the little light on the bottom, it trips as that water goes above the measuring point on the sensor. I believe this is our last slide. So that the capacitive is a non-contact discrete, very popular, been around forever, traditional level probe. There's a couple of ways to do it. You'll see up here on the left, capacitive, or I'm sorry, probes, conductive probes. So these are probes of varying lengths, similar concept to the capacitive, where you would have one with a short probe for your high level, and then another one of these devices with a really long probe. These can go way longer than 2 meters that stick down in the tank. And as the media touches those 2 probes, you close the circuit and you'll conduct across the probes, and it says the liquid level's here or the liquid level's here. These are discrete output, simple devices. Something like this can be used in a little bit of a dirty media because you've got conductive probes, as long as the media doesn't stick to your probes where it would get gummed up. The other technology that we use would be basically float switches. So think of the float in the tank of your toilet or your pool autofill. As that thing goes up, you've got a mechanical switch when the water level gets there, and it's going to give you a discrete or a relay output that says my tank is too high, my tank is too low, or I'm at some midpoint that I want to monitor. There's some pictorials on the right that kind of go through. Looks like we've got one over here with 4 or 5 probes, a couple with 3 here, high, low, mid. And this is just basic tank level monitoring, very inexpensive way to do tank level monitoring. And then you've got some interpretation devices that will take those outputs and turn it into a transistor, a relay, perhaps a Modbus or Ethernet register output value at that point. Questions on level probes? I kind of zoomed through the end there. I wanted to be respectful of time, 7:58. Open dialogue, questions, comments, applications. That's why we do this. Thank you everybody for your time, starting your week out with us. What else can we do to help out?
Chris, those level probes, again, I missed the technology behind them. How do you, is it a conductive thing?
It is. Those are conductive probes. So as the media goes up, you'll see this one over here. The easiest one to kind of envision it is this one here. You've got 2 probes. Once the liquid, think of putting your hand in a socket and your feet in a puddle of water. That's what's going on here. When the media touches those 2 probes, they conduct across each other. You're generating power, voltage, and current here. And then as a liquid when media comes here, it's going to close that loop and tell you that your media has hit the bottom of those 2 probes.
So it's a known resistance up the probe so that the probe knows where the media is on the length of that probe.
It's not an analog. You're only looking at the sensing device is just this tip. So once the media touches that tip, if it goes above, it doesn't care. Once it touches the tip, you get an output. So you would have,
okay.
Yeah.
It's a
Does that make sense?
digital. Yeah,
Correct,
digital
digital.
information, not
Yep.
analog. Got it.
Yeah,
Got it.
yeah. So that's why you'll see over here on the right, the probes are all different lengths. And when you order these, you order them in whatever length you want for your high level and your low level, or your mid level or whatever.
Well, your technology that you presented today, I know we traditionally talk about industrial applications. I deal a lot in the agricultural world, and a lot of this stuff is applicable there. So again, another huge market in California, because we are one of the leading agricultural producing states in the country. Fresno County is the #1 county for agricultural revenue in the United States every year. So also in the process world, of course, and we have some people like Ernie from the process world here today. Thanks, Chris. I learned a lot, and I sent out your presentation along with that data sheet on the FS flow sensor to the group. And next week we will be presenting on an important subject, even more important since I just got back from a trip to a huge oil refinery in Mexico, where I went down there with a whole shopping list of customer problems, and turns out that 9 out of the 10 issues on that list had to do with cable selection and incorrect installation on the cables. And we're talking about a multi-million-dollar installation with a whole bunch of variable frequency drives and a lot of people standing around because the C10, the electrical contractor, hosed up the cable selection and cable installation, and they're still in the process of sorting it out.
It happens a lot. It happens a
Oh
lot.
my gosh. We're on another project out in Arizona where we've been extremely careful on monitoring the installation and the cable selection, and that project still had some issues. So this subject next week is going to be really important. It's going to be on cable selection for pulsating power supplies, of which a variable frequency drive, a DC drive, a soft start are all big power supply, pulsating power supplies. And if you want these sensors to work that Chris presented on today, you're going to have your P's and Q's correct on your cable selections.
It happens all the time. Yep.
Yep. Chris,
Well,
thanks so much.
We're a couple minutes over. Thank you, everybody, for your time. I'll hang out for a couple minutes if anybody else has questions or applications, but have a great week, everybody.
Yeah, Chris, I'll call you after the presentation. Say hello to everybody. Time to go to work, and we'll see you next week.
Thanks.
Thank you, guys.
Thank you guys so much. And Pierce, if you wouldn't mind maybe adding me or at least letting me know the result of that conversation with the dew point in the enclosures.
Oh yeah, I was thinking about you when it came to mind. Yep, we'll talk.
Awesome. All righty, guys. Thank you so much.
Thank you so much.
Thanks,
Chris,
Chris.
you want to just
Yeah,
stay
you got
on
it.
and use this as a platform?
Sure, why not?
Yeah, okay. Anybody else can stay on if they like, but we got what's subject number 1?
I think we're going to talk about CanFab, and what else did we have? Probably want to talk about Bavaria a little bit, and I was going to see if oh, you're still recording, Pierce.
Oh yeah, never mind. Hang on, stop. I'll stop it.
I think Ray